Have you ever stopped to think about what keeps your feet planted firmly on the ground? Or what holds the moon in the night sky and keeps entire galaxies from just flying apart? It's this force we feel every single moment of our lives, but honestly, it's one of the deepest mysteries of the universe. It's gravity. And today, we're going to break down the rules of this incredible invisible power that shapes, well, everything. So, picture this. It's the year 1665. A young Isaac Newton is just sitting under a tree, probably thinking about, whatever brilliant people think about, and he sees an apple fall. Simple enough, but here's where it gets interesting. Newton asked this amazing question. If an apple falls, does the moon also fall? That one simple question was the spark that would eventually light up our understanding of the entire cosmos. You see, Newton had this incredible realization that the force pulling that apple to the ground and the force keeping the moon whipping around the Earth were the exact same thing. He just had to figure out the rules of the game. And what he came up with, it changed our understanding of the universe forever. And this is the big one, Newton's law of universal gravitation. And when he said universal, he meant it. It means that you, right now, wherever you are, have a gravitational pull on the Earth. But it also means you have a tiny pull on the Sun, on Jupiter, even on the most distant star you can imagine. Every single thing with mass is pulling on everything else.
So how strong is that pull? Well, it really boils down to this super simple idea. The more massive something is, like a planet or a star, the stronger its gravitational pull. And the farther away you get from it, the weaker that pull becomes. It's this beautiful, elegant relationship that governs everything from falling apples to orbiting planets.
Now this is where gravity gets kind of weird and fascinating. Unlike magnetism, it's always attractive. It never pushes things away. And get this, it's also astonishingly weak. I mean, the fact that you can pick up a coffee mug means your arm muscles are literally overpowering the gravitational pull of the entire planet Earth. The electromagnetic force holding that mug together is trillions upon trillions of times stronger. And yet, that same weak force reaches across the mind-boggling emptiness of space to hold entire galaxies together. It's wild.
Okay, so let's bring all this cosmic stuff back down to Earth. Literally. How does this universal law translate to that feeling of having our feet firmly on the ground? Well, it all comes down to a concept we feel every single day: weight.
Here on Earth, we can measure gravity's pull as this constant acceleration, which scientists just call g. It's basically the rate at which an object speeds up as it falls. And this is what gives us our weight. See, your mass is the amount of stuff you're made of. That's constant. But your weight, that's just the force of gravity pulling on all that stuff. And here it is, the magic number. On average, right at sea level, the acceleration due to gravity is 9.8 meters per second squared. What that means is, for every second something falls, forgetting about air resistance for a moment, its speed increases by 9.8 meters per second. It's a simple number that dictates so much of our physical world.
So if g is a constant, your weight should be constant too, right? I mean, that makes sense. Well, not exactly. What if I told you that you could actually lose a little bit of weight just by traveling, no diet required? And this is just a brilliant little quirk of our planet. See, the Earth isn't a perfect sphere. It actually bulges out a bit around the middle, at the equator. This means if you're standing at the equator, you are physically farther from the center of the Earth than if you were at the North Pole. And remember our rule? More distance means less pull. So you would actually weigh slightly less at the equator. So, we know gravity holds us here with this powerful, if slightly uneven grip. But humanity has always looked up at the stars and dreamed of breaking free. So what does it actually take to escape the gravitational pull of an entire planet?
Now, this isn't just about going up. It's about going up and not coming back down. There is a very specific speed you have to reach, a kind of cosmic speed limit you have to break to leave home for good.
And that speed has a name: escape velocity. The key phrase here is without any further propulsion. This is the speed you need to give something so that it can just coast away forever, winning its long battle against gravity's relentless pull. For our planet, Earth, that speed is a staggering 11.2 kilometers per second. That is almost 7 miles a second, or to put it another way, about 25,000 miles per hour. That is the price of admission to the rest of the solar system.
And here's the really wild part. It doesn't matter if you're launching a massive spaceship or, theoretically throwing a baseball into deep space. The escape velocity is the same. It's a property of the planet you're leaving, not the object that's doing the leaving.
So, what happens if you launch something really, really fast, but not quite fast enough to hit escape velocity? You don't escape, but you don't fall back to Earth either. Instead, you enter this amazing state where you're constantly falling, but you keep missing the ground. You start falling around the Earth. You enter orbit and join a cosmic dance that's been going on for billions of years.
When you look at a picture of our solar system, it might seem a little chaotic, right? But it's not. Every single planet, moon, and asteroid is following a very precise set of rules, a kind of cosmic choreography that was actually figured out long before Newton by an astronomer named Johannes Kepler.
Kepler laid out the 3 basic rules of this dance. First, nobody travels in a perfect circle. The paths are always ovals or ellipses. Second, planets act like cosmic figure skaters. They speed up when they swing in close to the sun, and then they slow right down as they move farther away. And the third rule connects it all. The bigger a planet's orbit, the longer its year is. Just 3 beautiful rules that describe the motion of pretty much everything in the solar system.
So why should you care about these 400-year-old laws? Well, because your phone cares. A lot. The GPS that tells you where to go, the satellite images that power weather forecasts, global communications, it all works because we understand this cosmic dance.
Okay, so this brings us to one of the most iconic images of space travel, right? Astronauts just floating effortlessly inside their spacecraft. We all call it zero gravity, but as we're about to see, that's not what's happening at all. Not even close. Seriously, think about it for a second. The International Space Station orbits just a few hundred kilometers above us. At that altitude, gravity is still about 90% as strong as it is down here on the surface. So if there's plenty of gravity, why are they floating?
The answer is honestly one of the coolest ideas in all of physics. They don't feel weightless because there's no gravity. They feel weightless because they and their ship and everything inside it are in a constant state of free fall. They are perpetually falling around the Earth. It's like being in an elevator when the cable snaps, but you just never ever hit the ground.
And this state of endless falling leads to some incredibly strange results. You can't just pour a glass of water because there's no down for it to fall toward. A candle flame will look like a little sphere because hot air doesn't rise without gravity. A pendulum just won't swing. This is the bizarre, everyday reality of life in orbit, and it's all thanks to gravity.
So we end on this thought. From the simple fall of an apple to the endless, blooping fall of an astronaut in orbit, it's all the same force. Gravity is what connects us to the Earth, what connects the Earth to the Sun, and what connects our Sun to the rest of the entire galaxy. It truly is the invisible architecture of our universe.